Um, it's called sigma. Okay. Um, so do you guys know Patrick Goss is?
No.
He's a physicist. You should study E&M.
I would have been in it.
They don't?
Yeah, they removed it. Yeah, me too.
They told me 3 days before school started.
Okay. Well, Patrick Goss is also the person that's known to have like Gauss's law, which is like I don't know like how quote me if I'm wrong. I'm not sure if I'm right, but it's Gauss's law is like how like diameter of the wire and how much like resistance can handle or something like that. Yeah, and something like that. So I don't remember exactly. I remember I studied in AP in that college of physics. Um, but but when he was a very little kid, like he was like I think like 6 year old, 7 years old, and he was a very annoying kid. Uh, so the teacher's like kind of like leave me alone, and he's like, well, you give me something
is
to
it
do.
like add up all numbers 1 to 100?
Yeah.
Is it that one? Yep.
So it's a 1 plus 2 plus 3 plus dot 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 to 100, and then the um the kid come back in literally like 30 seconds or like a minute, and he solved the problem, and he was like 6 years old, or 6 or 7 years old. I don't remember like exactly what age is, but he was really really young, and the kid only know how to add, but and he just come back, and the teacher didn't think he was right, so then he kind of says, well, um, the teacher kind of counted again by hand. I used the dumb way, and takes him like 15 minutes, and then he solved it, and then found out the answer is right. And back then, there's no calculator, there's no photo math, there's no nothing, right? So there's no way that he can cheat it, right? So,
It's 5,050, right?
yeah. Does everybody know the story of this, right? I talked about it last year, right? No? No? You don't know how they come up with this, Lyndon? No? Who doesn't know? Raise your hand.
Who doesn't?
Who doesn't know? Okay. Um, yeah, just like Ethan says. So Ethan, you can explain it to other people.
Okay, so basically, how it works is if you add 100 plus 1, and then 99 plus 2, 98 plus 3, those all equal to 101. So then you just would do that. So basically, what you could do is you could say a plus b times b over 2 equals c. So the minimum and maximum, so 1 to 100, divided by b, or you could, I guess you could say it's so
It's n.
yeah, whatever the
How many?
yeah.
How many turn are they?
Yeah. So because 100 divided by 2 is 50, it's 50 times 101, which is 50/50.
Does that make sense?
I did not do it. I feel like I did not do.
No, it's
a good
okay. You
job
did
with
fine.
that.
This people still don't understand. I can explain again if you people still don't understand. Basically, just instead of adding um instead of adding the 1 by 2 by 3, you add the first term and the last term, and second term and second to the second last term. So because this is 99, right? And this is 98. So therefore it's 3 plus 98. So they all have a uniform number. And obviously it's going to go down to 50 plus 51 is equal to 101. So totally there's 50 sets of number. If you have 50 sets of number, that 50 sets of number, then you got 50 sets of 101, so it'll be 50/50. Is that okay? So, and he was smart enough to do 50 times 100 is 5,000, and plus 1, so it'll be 50/50. So that is the thing. So we want to introduce sigma notation. The sigma notation is going to be like this. I equal to 1 and A1. So basically, you need to know this notation for Calc BC because at the end, like we deal with other sequence and series situation that you have to know this. So I'm gonna write down is equal to A1 plus A2 plus A3 and dot 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 to the A to the N. Is that okay? This part is called the lower bound. And this part is the upper bound. You can start with I equal to 1, or we can start I equal to 2. But the term number is always going to be like integers. So let's just say if I ever have something like this, I equal to 2 and 6 fi. What does that mean? That means you start at the low bound and you plug in the I. Right? So 2 plus 3 plus 4 plus 5 plus 6. You stop there. Whatever that is, that's the answer. Is that okay? So what will be summation of I equal to 1 to 4 of I squared minus 1? What do you think that is? Just write it out. So imagine if I would have plugged in 1, it would be 0, right? If I plug in 2, it's going to be 2 squared minus 1. If I plug in 3, that's going to be 3 squared minus 1. And I must stop at 4. And that's equal to 1. Oh, sorry, 3. Plus 8 plus 15. And it'll be 26, like 8 and 6. That's why it's sigma. Any questions here? Okay, so let's talk about this part. This part is kind of interesting. There's 2 different things here. Let's talk about some property first. Okay, let's talk about property first. So if I ever have a summation of I equal to 1 of n of kai, the k, just like integral, can be outside. I equal to 1 n of ai. So it's a very useful property. You can take the k outside. If it's some type of constant, you can take it outside. For this one here, summation of I equal to 1 times n of ai plus bi is equal to summation of I equal to 1 of n of ai plus minus summation of I equal to 1 of n of bi. So you can break up to 2 separate.
So it could be positive or negative.
It can be positive, negative, yes. Yeah, it's some kind of like sum and difference rule. Yeah.
Y can be positive or negative. Yeah, be bigger than the AI.
So when it's AI, does that mean that it's like function A
What?
being
Yeah, it
affected
can
by
be
I?
bigger than
Like, what does that mean?
So like, let's just say like I squared.
So like
No.
AI is like f of x type. kind of.
Yeah. And the other one could be like 2i minus 1. So they are two different sigma, so you can add up all the term together. Is that okay?
Oh, it's plus minus and minus.
Yeah, it's plus minus to begin with.
Is
So.
it only if I equals 1?
They can start with I equal to 2. You can start with just like lower bound integrals. You can start at
Okay.
10,
So these
Two,
properties
four.
still stay the same.
Yeah.
Okay.
but they have to be uniform, right?
Yeah.
If it's I start at 2, then both
Because
gonna
then it's
start
not
with
the
2.
same.
Yeah, they're both gonna start with 2. So I'm gonna give you some summation formula that's very, very important. Now this is probably the only time we're gonna use it. So some basic summation formula is summation of I equal to 1 of n of c. So you can have a summation of a constant, right? I equal to, let's say I equal to 1, 2, 3 of 4. So that means what? Your first term is 4, your second term is also 4, and your third term is 4.
So it equals NC.
It'd be Cn. Yep, good. So C is some type of constant, by the way. Second one, that if you have summation of I equal to 1 of n of I. Now this is just like Federico's situation. Is there must be a way to tell you. Now the formula he introduced is a little bit different. You have a first term, you have the last term. It's also known as the one that he's using is different than formula I'm gonna give it to you. Your formula is you learn it in arithmetic series in algebra 2. It's called arithmetic series. You guys ever learned that?
Oh, yeah.
So it's same thing. What do you say? Is a first term plus last term? It's actually the formula in arithmetic series is a1 plus a n over 2 times n. It's a first term plus last term divided by this, but this is not it.
But that's only if it starts with 1, right? Because otherwise it would be
You can work with every odd number with the situation, with your situation. It's called it's known as arithmetic series equation. I'll write it out because lay down. I'm gonna write out lay down because it might help you on SAT. It might not, but usually it's not covered. But this one is just basically n times n plus 1 over 2. But only work with the I though. Not odd number. Not like says or odd number can break up to two different things, but here it's gonna be n times n plus 1 over 2. Now let's try this equation with the 1 plus 2 plus 2, 3 plus all the way to 100. So in this case, it will be what? 100 times 100 plus 1. Do you see that? All over 2. Do you see that? So that's still 101 times 50 if I plug in this equation. Is this okay so far? Now the third equation is gonna be summation of I equal to 1 n of I squared. Now this one is n times n plus 1 times 2n plus 1 over 6.
6.
Yeah. Kind of weird number.
Very interesting. So if if I was equal to 2, the lower bound was equal to 2, would you change that formula to be n times n plus 2?
What'd you say?
So like if it was summation I equals 2, how would that formula change?
No, they don't have that formula.
Okay.
It just they only have
it's
I
only
squared.
if it starts with 1.
It's only for I squared. So sometimes they do have, let's say, if you have a you can break up to 2 separate one. Oh no, you cannot. Oh, sorry, I see what you're saying. You say the lower bound if the lower bound start at 2.
Yeah.
I don't think that formula will work. No, that won't work. But usually they start at 1. But I don't know what if they start at 2. That'll be a good question.
Because with that one doesn't. Yeah, I think how you would do it. Let me see if there's a way you could do it.
Yeah, you can try to come up with
I
it.
think the first one could apply if it's not I equals 1, as long as you put C and then parentheses n minus I. Or no, maybe not.
I won't worry about that right now, but we can worry about it in a second. But let me finish this. So you can also summation of I equal to 1. So we're gonna start with n. And there is a reason why I only care about start at 1, because right now, the reason why we need a summation is because we are doing definition integral. It start with a 1 rectangle, but we can break up to infinite amount of rectangle if n approach infinity. Okay, so right now we only focus on between 1 to, actually, in definition integral, it's only stem from 1 to infinity if we break up to infinite pieces. So this I cube is equal to n squared times m plus 1 squared over 4.
I think all you have to do for the I, for where it's just I to make it work, is you just do AI plus AN over 2 times n plus 1 minus I. And then it should work for any 2 numbers if it's.
If you start as I equal to 2.
So I think I
Yeah.
equals 2 would work if you just have that.
So yes,
Well, I got the Anthony approval, so
yeah, I'm trying to think about
because
when
this,
you have other
because the
situations.
reason I did the plus 1 is because if I equals 1, then that just cancels out, so it makes it so it's just that plus n times n. And then that way with 2 it becomes 1 and whatnot.
Okay. So if what we're gonna do is we're gonna show you some situation. Now, some situation that if you have a constant, you can take it outside. So for this case, that we can say, hey, let's evaluate summation of I equal to 1 of n times I plus 1 over n squared. Let's just say if you have n equal to 10, would it be, or 100, would it be of 1,000, would it be of 10,000?
What are we solving?
I'll tell you in a second. Okay. So this, you can rewrite this because remember that k, you can take it outside the summation. So you can say that's equal to 1 over n squared. And that's going to be I plus 1, right?
Oh, yeah, because n is constant.
Yeah, n's constant. Because constant can change in this case. I can plug in 10, or I can plug in 100. I can plug in 1,000 or 10,000 later. Now, what happened according to the property, right? Can I break this apart? So it'll be 1 over n squared times a summation of I equal to 1 of n of I plus summation I equal to 1 to the n
Plus or minus, right? Or no?
plus. In this case, it's
Just
plus
plus?
because the equation is plus.
Oh, okay, I see.
And that's 1. And also like 1 over n squared. So you can convert this using summation formula. What will be the summation formula? N times n plus 1, right? Over 2 plus n. I can distribute this. It'll be n squared plus n over 2 plus 2n over 2. Thank you. 2n over 2.
When you distribute it further with the...
I will add them together. So it'll be n squared plus 3n over 2. And I will even factor out n to cancel out 1 of the n. So it'll be n plus 3 over 2n. And that's my final answer. Now, if I ever want to find out if n is 10th, then I can plug in 10 into here and I can evaluate it. So I will do a chart for you. If I were to plug in 10, because if you upper bound stop at 10, then this value, the output, is going to give you like, yeah, whatever that is going to be 0.65. And if you plug in 100, then it's going to be 0.515.
That's weird.
Mm-hmm.
To actually solve the summation, will we take the limit of the answer to n approaching infinity?
Well, we're not there yet. Because we're going to, later on, what we're going to do is we're going to take an integral.
Oh.
And we're going to start looking at integral situations. So for some of you guys might not think how it works. So we're gonna show you that yes, eventually, hopefully, we can use limits all the way to infinity. Then the value is gonna be more accurate. So if you think about this, you say, okay, well, that's for those of you guys never take calculus before, I'm gonna show you is this. The two problem in term of calculus. First of all, it start with Isaac Newton and Leibniz. They start with the first thing is tangent line problem, which is the reason why they need to find a tangent line problem. It's actually speak of tangent line problem. My wife was asking me yesterday, and she was watching like 3-body problem. Have you guys seen 3-body problem? Everything it? Nobody ever seen it? Only 3? It's a pretty interesting show. I didn't like the ending, but
Yeah, it's kind of.
ending's kind of lame. But throughout, like I think the second season, it was pretty decent. It was like keep you guessing the whole time, and you trying to like figure out what it's trying to tell you. But it was actually pretty interesting. So the tangent line problem is trying to find out how fast the planet is moving, because if you can have a tangent line to a planet, then you can find out the speed of the planet. So I'm trying to like I don't know the exact history of it because I don't know enough, but just kind of imagine that you have you have telescope every day. You kind of observe the planet. Like, how do you decide how fast they can calculate back then using just a telescope, and that's the only like technology they have really. But they can calculate the speed. They can calculate things. I don't know how they do it, but the people in that age is pretty impressive, I feel like. But anyway, so the second problem is area under the curve, obviously. So area under the curve is start with like something like this, right? So let's just say I want to find the area under the curve instead of finding a tangent line. I can say from 1 to 4, and I can say I can break up to let's say it's 4 different rectangles, and I can say, hey, I can use midpoint, and that's will be midpoint. We're gonna talk about all this, by the way. We can talk about left endpoints. We can talk about right endpoints, because that's what we're gonna do later. And then we're gonna talk about the actual value. So the actual value is 5.25. Do you see that the bottom part, the last line, is the integrations? But you can do just say if I use left end, hold on, they should give you 4.265. It's pretty accurate compared to, it's not very accurate, right? It's a 4.26 versus 5.25. You see that area, the way you calculate area, there's still a lot of space opening. And then so the way to make this actually work is increase the n. Do you see what I'm saying? So if I increase the n, let's just say if I changing from n to 4 to n equal to 8, then you're gonna see the evaluation here on the bottom is becoming better because of 4.72 and 5.25. You say, wait, I don't think this is accurate enough. So we can, instead of do 8, then let's double that. Let's say, hey, let's change it to 16. And you can see that the space, the opening space, getting less and less. And you can see that the left endpoint becomes 4.97 as opposed of something that's relatively lower before. Now let's just say I'll break to 1,000 pieces. Right, this is 100 pieces. Let's see how accuracy they are. 5.25 versus 5.29. And that's only in the 100 pieces. So the idea is we're gonna try to break this to even more, so 1,000 pieces. So 1,000 pieces, you can see 5.2545, a little bit overestimate now.
Students should now be back from A level.
Rather than underestimate.
Well, that's it,
The
right?
purple is the division lines.
The left one's still a little.
Do you see like there are small edges on the side? That's what makes them that they have some extra areas. So it's 5.29. But again, if you can break to more pieces, the more accuracy that value is. And you can see that this is a, oh, I think, oh yeah, they had to spend some time to calculate. So this is almost to the 3 decimal places if we get to the 3 digits or 4 digits, 1,000 pieces. So the idea is what Newton did is Newton says, hey, what if I can break the infinite amount of pieces? Yes.
So remember time we reach perfection.
Yeah, it's only if you went to infinite pieces. There is always going to be a small deviation, depending on how many decimal places that you go out to, right? So right now is we do it break to 1,000 pieces. We are owning 4,000th of deviation, right? If you break more, and they're probably gonna spend more time to calculate. If I add more 0, they can't even calculate anymore, because do you see all this exclamation? The decimals doesn't have enough power to generate to 100,000 pieces and to calculate that value to the fine situation. But so what we're gonna do is we're gonna approach limit, because when there are 1,000 pieces of a million pieces, that small deviation becomes so fine, like you're gonna be a completely smooth curve instead of like those small edges coming out. I don't know if that makes sense, but hopefully, I don't know, Jing, does it make sense to you? Raphael? Krisha? Okay. And everybody that in second year? Okay. So what we're gonna do is we're gonna start building on that. So that we're gonna use a we're gonna use right endpoints. We're gonna use the right endpoints. So this is gonna be one of your homework questions. It's the first time I'm gonna ask you to do a lot of algebra. So we want to find the area of x squared and we're gonna do it between 0 to 2. Now, what you can do is that we're gonna answer also Isabel's question. Isabel says, how is that gonna be accurate? So what we're gonna do is we're gonna use two approach. We're gonna use right endpoint approach. We're gonna use left endpoint approach, and we can average both. Right? Hopefully they average both, and that's where squeeze theorem comes in. Because squeeze theorem is if you go from the left endpoint and right endpoint, hopefully they squeeze in the middle where you're gonna be the same. And we're gonna figure out if that's true. So the definition of integral of integration of a to b of f of x dx. So for those of you guys never seen definite integral, is basically I want to just area under the curve. It's not indefinite integral. Indefinite integral, you're gonna get an expression of a function. And in this case, you're gonna get an evaluation. Okay? It's equal to, as the limits n approach infinity. Is that okay? F to the, we're gonna call that mi, and in this case, we're gonna call it mi as the right endpoint. And delta x. Oh, and there's a summation. Sorry, I missed a summation. I equal to 1 to the n. So what will be the delta x? In this case.
Changing the x to 2.
So the change of x, which is what? 2. Over n, right? So actually it's b minus a over 2, b minus a over n. So it'll be 2 over n. Does that make sense? So it depends on how many pieces. I can break to 10 pieces. Then each pieces is going to be what? 1 over 5. Does that make sense? I can break to 100 pieces. Then each piece is going to be 1 over 50.
Why is it over n?
And it's we're going to assume that we can break the infinite amount of rectangle. Right? How many rectangle I want to break down to? If I want to break the 4 rectangle, then I have to add up each individual one. But we're gonna say it's n because n is gonna be, we hopefully that we can reach that n to infinite. Is that okay? So we know that this is gonna be 2 over n. We know that this is gonna be 2 over n. Now we're gonna get say right endpoints. Well, we want to plug in each thing, right? So if I were to plug in each thing, so what is mi? So what we're gonna do is figure out what is mi here. Mi is gonna be your starting point, which is 0.
Oh, so it's the left end.
No, right endpoint. We're gonna do right endpoint right now. We're gonna do left endpoint in a second.
But how is it the starting? How is it 0?
Plus, because you had to add a first base. So in this case, it's gonna be I times 2 over n. Because I start at 1, so it becomes 1 space away from 0 because we use right end. We don't use left end. Does that make sense or no? Imagine like this, right? Imagine I have some curve that if I have some curve, I start at 0. I'm using the first space, whatever the first space, and I'm gonna use this to draw out. Does that make sense? So I needed like 0 plus that space. That space is 2 over n. And I is just a sequential number. I don't know what's it, but is that best word? Yeah. It's a number just in order. 1, 2, 3, 4, 5. Is that okay? Now I'm gonna plug in. I'm gonna say summation of a to b of f of x dx is equal to limits as n approach infinity of summation of I equal to 1 and n of f of 2I over n delta x. How many people are lost? Raise your hand if you do. Okay. Am I just gonna start a right endpoint? We're gonna start a right endpoint. So we're not using the left endpoint. The left endpoint will get 0.
Oh, you mean right point, the
Right Riemann sum.
approximation, the Riemann sum.
The
Okay.
Riemann sum. So you start at the
I
first.
thought you were
You
talking
don't
about
start at
the-
0
I thought
because
you were talking about the point of the graph.
right side of the graph, right? So this is gonna be the delta x because you're adding 1 delta x because we start with I is 1. So we use a I as a first point. So right, that's why I say I don't worry about I equal to 2 because we start with I equal to 1. The first point that I'm gonna plug in the evaluation.
We want to change that delta x at the end to 2 over n before.
Yes, we're going to. Yeah, I can do that now. You're right. This one's gonna be 2 over n. Is that okay? Now I'm gonna go to limits as n approach infinity. I'm gonna pick a 2I over n. I'm gonna plug into the function. So that's gonna be square times 2 over n. And oh, sorry, I forgot a summation.
Wait, why? Oh, okay, because it's f of.
Yeah, f of that. Because I'm plugging the function. I'm plugging the each spaces. Because I is 1, I equals 2, I equal to 3, I equal to 4. I'm just adding each individual one.
Oh,
And what?
because f of x
Okay.
is x squared.
Sorry, let me rewrite this. It's all crumbled together. So this one's summation. Summation of I equal to 1 to the n. And this is 2I to the n square and 2 over n.
And 2I to the n came from mi.
Yeah, mi is basically spacing, each space.
That makes sense.
Yes, Corbin? Square is because of function, f of x equal to x squared. So I'm plugging 2I over n into the space.
And the reason that n is going to infinity.
Because
The
we want to
reason
break
that
the rectangle. We
is
want to
is
break
that
the.
why we're dividing by n?
What?
Is the reason we're dividing by n because it goes to infinity, so it makes it so it's just like little
Exactly.
itty bitty pieces.
Yeah,
Okay.
that's why you have a limit there. That's why we study the calculus start with the limits.
So it's almost like doing infinite zeros to get something, in a way.
Infinite
Infinite
rectangles.
that it's almost zero.
Because this, I didn't explain this carefully. Because this is gonna be the height of each rectangle, right? F of something, where you will get an output. That's the height, right? And I'm sorry I missed this one. It's gonna be the width. So basically, I'm adding the right endpoint of each height to each width, and to infinite amount of pieces. Width is 2 over n. It's delta x.
Okay.
Is that okay? Okay.
I think so, yeah. I'm starting to conceptualize.
So it's like the same thing as like last year when we add the area of the rectangle but just in a different notation. Like last year we
Last year we just do approximation. Last year it's different because we only do like 4 rectangles. Yes.
So the 2, you did 2 minus, like, why are we doing b minus?
B minus A is each width because we're not sure we're gonna do n equal to 2 or n equal to 5, n equal to 1,000 because we still says we're gonna let it as to be a number that we can approach something. So the between integrals between 0 to 2 is just 2 spaces. But if I want to break out 2 triangles, so it'll be 2 over 2. So it'll be each width is going to be 1. Now, if I want to break 4 rectangle, guess what? It's 2 over 4. Then each space is going to be half. Does that make sense? Imagine that if I have like this. Huh?
So you're trying to get n to infinity, you don't want to be very wide. Like,
Yeah, I want n to be very, very small. 2's matter because you have you do integrate between 0 to 2. So if I have this, right? If I break the 2 pieces, then this 2 over n. Why? Because this is 2. If I break the 2 pieces, then it's gonna be 1 because it's gonna be like this. And it's gonna be, well, right endpoint is gonna be like this and this, right?
So the definition of integral only ever use the right and
You can use right and left, and we're gonna do left afterwards.
Okay, so there's multiple definitions.
No. You squeeze them. You use the right endpoint first, but if you break the infinite pieces, it doesn't even matter right or left. But we're gonna show you that even the small pieces can be working left and right.
It is.
No, it's not trapezoid. It's a rectangle right now.
No. He's saying when you do the average of the 2, that gives you trapezoid.
Yes,
Okay.
it'll be trapezoid because that's why we have trapezoid rule come in.
Okay.
Because trapezoid is more accurate, right? We can be more accurate.
There's a lot going.
So now I'm gonna start dissecting everything here. So I'm gonna do the math. I equal to 1 and this is gonna be 2 times 2 is what? 2 times 2 is 4. 4 times 2 is 8. So it'll be 8i squared over what?
N cube.
N cube. Okay, good.
Limits to there. Right?
So n cube
Oh,
can
yeah,
bring
yeah,
out, right?
limit approach infinity.
And same with 8.
And same as 8, good. You're 2 steps ahead, so that's gonna be good. So this one I squared. Now, do we know the formula for I squared?
Yeah.
So what's the formula for the I squared?
And plus 1.
So this becomes a summation formula. So it'll be n times n plus 1 times by 2n plus 1 all over 6. 8 over n squared when limits n approach infinity. Limits n approach infinity. N cube. You're right. Okay, so now I'm gonna distribute the top. Now, do I care what happened afterwards? Not really, but just in case, I'm gonna distribute the top. So that's gonna give you n squared plus 1 times 2n plus 1. This n squared plus n, right? So it'll be 2n cubed plus n squared plus 2n squared plus n. And times by 8.
Having to write diagonally.
Right? So that's equal to 8. I just distribute this.
Yeah.
And that's going to be 8 times 2. So it's going to be 16. N to the cube. Is that okay?
Yeah.
Plus this 2 add together is 3. So it's what? 24n squared. Thank you. And plus 8n over 6 n cube. I missed an n cube here.
And then you can factor out an n.
No, you don't need to factor out. You divide it by highest degree of a denominator.
Oh, because it's infinity.
Yeah.
So,
I mean, 16 over. He's never 6. Oh my god.
So it'll be 16 over 6, which is 8 over 3.
Yeah.
which is what's integration of an x squared dx between 0 to 3 or 0 to 2?
16 over 6. My
Which
gosh,
is a over 3, right?
it was quite a bit there.
What's the last time we What's the last
Now I do right endpoint is because it's harder. Left endpoint, I mean, it's easier, sorry. Left endpoint is harder. Now, since you guys says, well, if I bring the infinite amount of pieces not good enough, I'm gonna do it with the left endpoint as well. Okay, so left endpoint is a little bit harder because we're gonna notate it as left endpoint here. The left endpoint is gonna be integration between a to b of f of x dx is equal to limits as n approach infinity summation of I equal to 1 to the n f to the m non-capital delta x.
But what's the?
Non-capital. So this is the left end.
Oh, the capital means something. Okay.
The capital M here.
Okay. Let me change that. 'Cause I
Is-
just wrote down a lowercase m before.
This is the right.
Wait.
Yeah. Wesley picked the wrong day to skip.
Truly.
actually
Okay, so now the non-capital MI, but the delta x still the same, right?
Yeah.
Because still the from where to where, that is gonna be 2 over n.
Yeah. Well, we don't have like active question over.
Oh, okay. The delta x is still the same.
so mi is gonna be
So is this okay?
Yeah.
So what will be the starting point? The starting point is still at 0 because this is where you start. Now, if you do integration between 1 to 3, then that's gonna be 1.
Yeah.
Okay.
So this is starting is a 0, but since the left endpoint, your first space is gonna be I minus 1 over 2.
because if it's 1 then it would be 0.
Yeah.
Since 11.
Sorry. It's gonna be I minus 1.
Oh my god.
Sorry, I minus 1. Sorry. I think I write it wrong. Times what? 2 over n. And then you can finish the rest today. Because I don't have enough time. But anyway, you're gonna have, let me write down the first line for you. The first line is I equal to 1. N of f
It's still
2I minus 1 over n
We know the answer.
times 2 over n. And then you're gonna expand them. This one is a little bit harder, but I'll send a picture if you already have problem.
So
Yes.
you can just get rid of the f after you like square it because it's f.
You square the inside, expand them. It's just algebra is very messy here. Yeah.
Joy. I love messy algebra.
If you're interested, I'm gonna finish this, but if you have to go lunch, I understand.
I would normally say, but today is Friday, so.
What? Oh. I'm gonna record it then. I'm streaming right now. Hold on, let me double check. Yeah, it's streaming.
I'm locked in mystery. Are you gonna finish it?
Yeah, I must finish it. So this one is gonna be limits of n approach infinity. So limits as n approach infinity here, summation I equal to 1 and This one's gonna be 2i minus 1 to the n to the square times 2 over n. Yeah, no, it's just understanding how small thing works. So now if you pay attention that this part, this square can be pulled out. So can be pulled outside the thing. So ideal is still gonna be the same as before. So not 4 over n squared. It's actually 8 over n cubed.
Okay, there's two of them.
So let's just say this is 2 over n, right? And it's 2 squared over n squared. So that's going to be 8 over n cubed. So it'll be 8 over n cubed. Limit n approach infinity. Summation I equal to 1. N of I minus 1 squared. And then 8 over n to the third. This one is going to be summation of, well, we're going to expand this, so it'll be I squared minus 2i plus 1 between I equal to 1 and limits of n approach infinity. Hi, how are you? What's your name? Isabella. Welcome here. Have a seat. I'm making videos.
We're gonna leave in like 2 minutes.
Oh, okay.
Yeah.
All right. See ya.
But yeah, this is just the proof, Mr. Ye.
The
I'm
proof.
not lying.
Just kidding.
Be here.
It pay you to be here. Okay.
What purchase for that?
Huh?
You remember what I told you?
Yeah. Are you?
Who's that girl? Who's that white girl? She's not white. What is she? No, I mean this girl. Never met her.
You've met me so many times. She's here like every day.
No.
Yeah. I'm not
This-
in your class, but I come here for
This is like first time I seen her.
No.
Wait, this is all here.
So you can break down to 3 separate integrals. So
I squared minus and 2 and 2i and then 1.
I know, so hard for me to write. Yeah.
surprisingly, this question is actually like UCF actually want to write everything out. Yeah, the definition of the integral, and they want you to write everything out. So this one will become 8 over n to the square.
Remember all the formulas for this reason?
Unfortunate for this one, yes. I might give it to you. I don't know.
Yeah. There's so many. Don't you have to give a block?
Now this is at limits at n approaching infinity. Now if you pay attention, here it's n squared, here's n. If you divide by n cubed, pretty much all this is gonna go away. The only thing matters still the same as before is this part, because this part is gonna go to 0. Because n cubed is larger than this, and n cubed is larger than this. When you divide it back out, n approach infinity, it's still gonna go to 0. So it's still same as before. This part is still same as before, because this part is gonna go away. Does that make sense? Because the top part is only n squared.
High
as denominator.
Yeah, and this NQ is right here. So
it's
this
16 over 6 again, right? So it's just
is gonna be 16 over 6.
8
Yes.
over 3.
Yeah.
Mhm.
Wait, but shouldn't it be different from the right Roman center?
No, it's the same. If you break small enough pieces, it doesn't matter left or right. It's still going to be the same. So at this case, it's still going to result the same because this part is still the same as before. And that's 16 over 6, which is A over 3.
There's only two.
Wait, does Cooper go over it?
I think we went over it like for a little bit, and then I mean I got it from Leonard, Professor Leonard,
Yeah, he's great.
It's just the answer. Oh.
and then the MIT
Don't look at it.
lectures go into a lot. So I watched those.
Okay, that's it.
Triangle.
Because all this is going to go to 0. Does that make sense? All those are going to 0 because this one here, it has n to the q. If you n to the q here, if you distribute go to infinite, this is all going to go to 0. So all those things doesn't matter. It's still certain things matter there. Which is, I only look at the highest coefficient. In this case, it's going to be 2nq times 8. Because I hear basically is 2nq times 8 over 6nq. And this nq cancel out is still 16 over 3. Still, because you only take account into this, right? Versus this. So it's nq over nq. But everything else is going to go to 0. And I'm going to go get Subway.